Welcome to today's colloquium. This is the first colloquium of the year. It's a great pleasure to have Professor Xiao-Gang Wen to be here to deliver the talk. Professor Wen is a CISO and India Green Professor at MIT. He is a world-leading expert in kinetic physics. Dr. Wen studied supersymmetric theory at Princeton University, where he received his PhD degree in '87. Then he switched his research field to kinetic physics at Santa Barbara before joining MIT. Professor Wen introduced the notion of topological order and quantum order to describe a new class of matter states. This opens up a new research direction in kinetic physics. Then he pointed out that topological order is nothing but a pattern of long-range entanglement. This led to the notion of symmetry-protected topological order and its description by group cohomology of the symmetry group. He has received lots of awards and prizes. Currently, he is also the Distinguished Research Chair and the Isaac Newton Chair of the Perimeter Institute. Now let's welcome Professor Wen.
Thank you very much. Thank you for inviting me here, and also Happy New Year. I didn't expect in January the temperature can be 24 degrees. So it's really a nice place to come. So today I'm going to discuss some recent development in kinetic matter physics. But however, I try to start from some big picture. Try to explain those progress. And so we know that our world is really, really rich and beautiful, and we want to understand the world. And but what do you mean by understand? You know, what this understanding really means. So actually, the way we understand the world is through the cycle of discovery, unification, more discovery, and more unification. Because when we explore the world, we discover a lot of phenomena. And when we have more and more phenomena, we get confused because why we have so many new things. So we try to understand them. Understand them means maybe those rich phenomena only coming from a few things, a few principles or a few rules. So that's kind of unification. Then after we unify, then we discover even more phenomena. So we need more things to understand them, and then we get confused. Then we want bigger unification. So therefore, this is kind of cycle for unification and discovery, kind of describe our development of a theory for our work. And so in history, there's a few big unifications. We can call them a revolution in physics. Actually, those unifications have some kind of characters, you know. So basically, each unification, we can say that brought us into a new world. By new world, that really means that some fundamental concepts are changed. And also, this old way of thinking and even this old language to describe things does not work anymore. Because the concept changes so much, we have to change even language on the way of thinking. And we also need to usually, certain new language and new way of thinking usually means introducing new mathematics to describe the new world. So that's kind of character of a revolution, you know, in physics. So the first revolution we can say is a mechanical revolution. Okay. They unify the phenomena of falling clouds and also the planet motion around the sun, you know. And so nowadays we think, okay, that's all gravity. But if you imagine, I don't know how many years ago, say 200 or 400 years ago, and 300 years ago, you know, we see the phenomena of things falling from the sky, and also star, planet moving in the sky. It's hard to believe these two phenomena are the same thing. And so Newton say, they unify these two, they say they are the same thing. And then, in that case, in Newton's world, our point of view is that every object, all the matter are formed by collection of particles. There's some kind of idealized matter, just a collection of particles. If you understand how this collection of particles move around, we can understand the motion of all matters. Okay. And so Newton have this theory, say F equals ma is a theory, but the mathematics is calculus. In Newton's time, the mathematics to describe his theory is not invented yet when he developed his theory. So Newton has to invent new mathematics at the same time developing his theory. Okay, and so that's the first time that the physics and the mathematics can develop together, or you can say the physics is ahead of mathematics. So when physicists need a mathematical formalism to describe a phenomena, that mathematical formalism had not been developed yet. So the physicist has to develop mathematics at the same time. And the second revolution, I would say, is like an electromagnetic revolution, which unified the phenomena of electricity, magnetism, and the light. And that's also quite amazing. Again, these three phenomena looks quite different, but however, under this new revolution, they became the same kind of phenomenon. Okay. And however, in this new world view, we have wave-like matter now. In Newton's world, all the matter are particle-like. So, but in Maxwell's world, we have, in addition to particle-like matter, we also have wave-like matter, and which is electromagnetic wave. And the motion of wave-like matter is described by Maxwell equation. So there's a new kind of a matter. And the new mathematical language for this electromagnetic phenomena, for this wave-like matter, actually is a fiber bundle or gauge theory. So that is a new mathematics. And then the third revolution, I would say, is a relativity revolution. Again, the unification is quite amazing. The space, time, and the gravity is unified. The gravity is the interaction, and the space-time is stage where everything kind of moving around. But somehow this is unified. And the principle behind this unification also pretty simple. Is that the downpool we felt inside the accelerating accelerator, Einstein said, is the same as the downpool we felt due to the gravitational interaction. You say these two kinds of force is totally equivalent. There's no way to distinguish them. But however, in the accelerating accelerator, the downpool field actually coming from the changing of a coordinate. It's like a coordinate transformation. And so it's something geometrical. But certainly, near the Earth, the downpool field is due to gravitational interaction. So I say these two is the same situation. So therefore, we can simulate all the gravitational interaction as some kind of changing of a coordinate. It's some kind of accelerating coordinate. So this is basically, this idea that led to this notion that actually the gravity and the curved space-time are actually the same kind of equivalent and the same concept. Okay. And Einstein did not introduce new kind of matter, but however there is a new kind of wave-like matter. We still have wave-like matter, but after Einstein, the gravitational wave became the additional wave-like matter. Okay. And this wave-like matter satisfies a different equation. It's the Einstein equation, not the Maxwell equation. Okay. The mathematics will be the Riemann geometry. And in both, in this case, in Einstein's case, the mathematics of Riemann geometry is invented maybe 50 years ahead of Einstein. So when Einstein developed his theory of gravity, he do not need to introduce or invent new mathematics. He just need to take the known mathematics and apply that to his theory, and that will work. Okay. So, so the fourth revolution I will say is a quantum revolution. In this revolution, we don't have a single hero. So we have a bunch of them, and this one is I would say this one maybe is the most impressive revolution because it's a revolution nobody like it because the physicists don't want to go there, but it's dragged by the phenomena, by the experiments into there. And, you know, we can unwillingly and forced to go there to propose this kind of a theory, and it's unified this phenomena like this hydrogen discrete spectrum hydrogen atom, and this the interference of electrons and the black body radiation. Again, it's a very different kind of phenomena. Somehow can be explained and unified under the same theory. And the new worldview is very impressive, actually. In the quantum revolution, the particle-like matter and the wave-like matter became the same. So there's no longer a distinction with particle-like matter or wave-like matter. And so in a sense, the matter is neither particle nor wave, and both particle and the wave. So it's a little bit strange and hard to understand. So, but that's actually reflect the things that the concept of existence is not what we thought it is. It's actually what do you mean by existing? Existence is very, very tricky, and so that's why it's the concept of matter or something there is it's very strange, you know. Okay, and so we can call them particle wave-like matter, and something which we are not familiar with anyway. And the new mathematics to describe this word, the quantum word, actually is not a calculus. It's a linear algebra. So actually, if you believe that our world is quantum, we can abandon calculus. We don't need a calculus. Actually, it's not described by calculus. It's actually described by linear algebra. Okay, and certainly linear algebra, you know, in this case, a mathematician again is far ahead of physicists. The linear algebra was invented a long time ago, and the physicists just use this linear algebra in quantum theory and to describe it. Okay, and but in this talk, so what I try to explain is that actually there is a second quantum revolution, or maybe we are experiencing a second quantum revolution. And to explain this second quantum revolution, so I think we can using this movie Matrix. I think most of you, at least young people, probably saw this movie. And in this movie, it's described two worlds. One is a real material world. That's the world we are familiar with. But then there's another world. It's called it's a virtual world, which is only inside the computer. So the virtual world is formed by the bits, you know, in a computer memory. You know, it's a virtual world in the computer where everything is formed by bits. Okay, but this movie try to bring out the message is that this virtual world inside computer can be as real as a real world, you know, real material world. Okay, so that is the message of the movie. And but however, I want to say that this movie is not revolutionary enough. So actually, our world is much more strange than the movie. Actually, our world is the information world. There is no material world. So what we thought as a material world is actually an information world. And so the so-called real world we have is actually information. So this is the only thing we have. Okay, everything is here. There's no real world, just information world. So in some sense, we can say we live inside a quantum computer. Quantum is important. Certain matrix only describe a classical computer, but actually we indeed live inside a virtual world computer, but live inside a quantum computer virtual world. In some sense, in the setup of the movie, that's what our world is really this virtual information world. And so certainly you may say, well, what do you mean by that? Those just looks like something totally irrelevant philosophical thought. And so first, let me just make a point that usually the information and the matter are very different. And so the information is viewed as some kind of a property or some feature of a matter. So there's something like information is carried by matter. So there's information is a carrier. Okay. But however, if we believe in the quantum theory, the essence of quantum theories already tell us information and matter is the same thing. So quantum theory, essence of quantum theory really says that we should unify information and matter. And why? Because you know that the frequency, frequency actually is a property of information. Means something changed. Frequency means something changed or how fast it changed. So therefore, information and the changing information really correspond to the frequency. However, quantum physics tell us the frequency is energy. And this is very, very important. But energy is a property of matter. Or another way you can say that according to relativity, energy is mass, mass is matter. Even without relativity, energy itself can be viewed as matter. So energy is a property of matter. So frequency is a property of information, energy is a property of matter, and the quantum theory say the frequency and energy is the same thing. So basically, let's really say that information and matter are closely related at least. If you go one step further, you can say information is matter, matter is information. Okay. So it's not surprising to say it looks like matter is information is a very radical statement, but actually it's not radical at all. If you truly believe quantum mechanics, you have to accept that. Okay.
Excuse me, on the computer this may be easy, but still in the real world, there's no dynamics in the slide.
Yeah, I will explain. Yeah, so that's the rest of the part. So that's basically this picture. So those are information. That's a 0 and a 1. That's information, and those are matters, and so they are the same thing. Okay. And but now let's be serious. Do you really believe in that? And so whether our world is really information world or not. So one way to make this more concrete into a physical question instead of philosophical question is that we can ask by view whether starting from a simple information of qubits, can we obtain all kind of matter? Means all kind of elementary particle. Whether all the elementary particle can be viewed as arising from pure information. Is that possible? Okay. So actually we have a very, very simple picture here. And suppose we live in a very simple universe. We only have one kind of elementary particle, which is a spin zero boson. Inside such simple universe, then obviously this kind of elementary particle, scalar boson, can come from information. Here's the picture. It's that the space, our space, we view our space as a collection of qubits, just 0 and 1. So space itself is like a medium, it's a qubits. And if there is no qubits, there is no sense of a space. So you cannot ask what between two qubits, because the sense of a space is coming from the qubits. Without qubits, there's no space. Okay. And then we can say that if all the qubits are in the zero, that's like a vacuum. That's a background. If one of the qubits equal to one state, then this represents a spin zero boson. And this qubits one can move around like this spin zero boson moving around. So therefore, using this picture, we can easily obtain this identical. Actually, this spin zero boson are identical particle. So they're identical particle and spin zero boson. So therefore, if our world have only one elementary particle, one kind of elementary particle, which is spin zero boson, then we can say that maybe our world is an information world. The space is formed by qubits, and then the excitation is from 0 to 1. This kind of excitation representing the elementary particle in that universe. So then everything would be fine. So so therefore we can explain all the phenomena using this information point of view. So that's a basic idea. Yes. So that's what I mean by the world is an information world. It's just that the space, the whole space is collecting qubits. Then everything we see are just a collect motion or excitation of qubits. So we can using qubits to explain all the phenomena in our world. So that's what I mean by we live inside a quantum computer, information and the matter, same thing. This is what I mean. Yes.
So this world, you cannot define magic.
Hmm?
You cannot define magic in this world.
You can.
You can.
You know, matrix defined by this so-called massless excitation. So once you have a massless excitation, then you can measure, you have a sense of distance. You can say how we measure distance, how we measure time. You just send out light signal and bring it back. So once you have those mobile excitation, you can define that. And but actually, you touch a very important question is that where metric comes from. Later, I try to argue that metric comes from entanglement. But our world is much more complicated. Elementary particle in our world is not just a scalar boson. We have identical particle, but should I say none of them are scalar boson? Maybe I shouldn't say that. There's Higgs, and so our world, we already unify many things. So at the moment we can say that maybe there's 7 fundamental features, and so like we have an identical particle, we have a spin 1 boson, but which only have 2 components. Usually spin 1 should have 3 components, but our spin 1 boson is very strange, have only 2 components, which is a photon basically. We also have a particle which carries something called Fermi statistic, which is really strange quantum mechanical property. And those particles also carry fractional angular momentum. And also we have this so-called strange phenomenon where only maybe left or right fermion couple to SU2 weak interaction. And this phenomenon is discovered by, theoretically proposed by Li and Yang. And certainly we have a reverse symmetry. And we also have a spin 2 boson with only 2 components. Usually spin 2 should have 5 components, but strangely we don't have 2 components, and those are gravitons. And so those are ingredients of our work. It's not just simply a scalar particle, scalar boson. It's not that. We have all these things. And then the challenge is that can simple qubits produce all those phenomena? Basically, if you think about this picture, so if you view our world as like this, can we have a photon, electron, weak interaction, graviton? Can those elementary particles emerge as a collect motion of qubits? Qubits is very simple. It's boson actually. Qubits are bosonic, but can fermion arise from purely bosonic qubits? So for a long time we thought, oh, this is hard. It seems impossible. Okay, and so actually in some recent last 20 years or so, we feel that the answer is a kind of a yes. So so actually the first 6 probably 6 wonders indeed can come from the qubits. Provided that you'll say the qubits have a property called the long-range entanglement. If the qubits have a long-range entanglement, this collective motion of qubits can indeed produce these first 6 properties. And at the moment, we still don't know whether we can produce the graviton now from the collective motion of qubits. So we are still working on that. But so this is not known. But the first 6 wonder can be produced by the qubits. So therefore, this kind of picture represents not a grand unification, that word's already been used, which unify different gauge interactions. So let's call that a great unification. So which unify all the gauge interaction and all the fermions. Actually, fermion electron quarks is unified with the gauge boson in this picture. Yeah, they all come from qubits. Qubits is the only thing there. And fermion, gauge boson, all coming from collective motion of qubits. So this unification is a kind of a bigger unification than the grand unification. And so certainly the new point of view is that our world is a quantum information world. So this kind of explains the meaning of existence. This so-called particle wave-like matter actually is a qubits. Everything is a qubits. Okay. So is that possible? How this picture works. So maybe let's explain entanglement through some examples. So entanglement here play a very important role. So what is entanglement? Okay, so entanglement is like 2 spins, 1 up, 1 down. This is called Dirac parallel state. By definition, this kind of quantum state is called unentangled. And then this up, down, plus, down, up is entangled. So that's kind of we don't have a classical picture for this. It's somehow entangled. Okay. So we may try to make a more entangled state, like up, down, down, plus down, up, down. So look at it. More superposition, the more entangled. But usually when you do something, if you're too greedy, you will get nothing, because this state is unentangled. Because this particular state actually is up and down states, up plus down, tensor product up plus down. So basically it's a spin in x direction, tensor product is not a spin in x direction. So this is unentangled. So entanglement is a little tricky, sometimes not so obvious, but they do exist. So like this one is indeed entangled. So no matter which base you write in these states, you cannot write these states as a product states, no matter how you choose the basis. But these states, you can choose a basis that in some other particular basis is a purely product states. Okay. And in condensed matter, we study a lot of quantum systems, like antiferromagnetic states. The antiferromagnetic state, like spin up, spin down, spin up, spin down, they are unentangled. And we can also study also called some kind of dimer solid, which is the spin up, spin down form a singlet. And this spin up, spin down form not singlet, and etc. And this state are entangled. So this one is unentangled, but this state is entangled. But however, this state is not long-range entangled. It's only short-range entangled. Remember, I have emphasized that to explain this kind of wonders, we need so-called long-range entanglement. But so far, I only explain what is unentangled or this short-range entangled. The reason this one is a short-range entangled because although there is entanglement between this speed and this speed, if we group these 2 sides, we think of these 2 sides as one effective site. Then among effective sites, there is no entanglement because it's just a Dirac product of spin singlet. Okay, so you get some notion that there is unentangled states, there is a shorter entangled states. And to explain the wonder of our universe,